Yes, started. Hello guys. Welcome to my video on W542 video on lab, the second video on second lab video on W542 lab series. So this is the second part of the W542 lab. Here in the previous two videos we covered how to establish a simple network, a server client network with a router in between using VirtualBox. Here we are just going to replace VirtualBox with AWS and use all the hi-fi features that AWS offers. So we are going to basically do everything in the cloud, no local machine. So that's the only replacement to this project. Compared to the previous project, in this project, this is the only replacement. You use AWS, right? So let's get right to it. So these are the specifications. Let's come to it once we start. Once I start the demonstration, now let me just walk you through the network topology. The network topology is same as before. You have a server, you have a YoS router, and you have a client, and you have to establish a simple local network connection between them. So the server has two interfaces, just like in the previous lab. You have a local interface to connect to the router and client. You have an NAT interface, which is used to SSH into it. You may see that I have also highlighted public IP here. Why did I do this? Let me walk you through once I show you the demonstration why I have included a public IP. Public IP is basically um, the real public IP address that Amazon allocates that particular instance, which allows you to SSH into it. In the previous case, why did we not use any public IP address? Why? Because we basically used our local version. Uh, all the instances were just virtual images on our local machine. So we are able to internally connect. Whereas in this case, we just don't just just having the uh, just having a private NAT address doesn't do it. We need to have a public IP so that we can surely connect from our system to Amazon's the server which runs this instance. Right. The same goes for router as well as client. The rest are same. You have the server, you have the local IP address. Sorry, you have the local IP address, and this is the NAT address mapped to a public IP. And here we have our this is the first subnet, just like how we used intnet1 to label our virtual connection in the previous project. And we have the router, and the router has two IP addresses, one for the left interface and one for the right interface. All these are local IP addresses. And then here is this is the second subnet, intnet2, as we used to call it in our previous lab. And then we have the client. So, okay, I think I failed to mention this. The client has an IP address, IP address I used. This is the local IP address of the client, right? The client has a NAT. So all these NATs are just used to SSH into these instances, these remote instances, just for our convenience. We remotely control these machines. And then this part is the actual network that we are interested to establish. We don't care about that. Once we once we configure our internal network, our only aim is to send packets through server. In this lab, we just instead of sending packets, we use IPOF measurement, which sends packets, UDP and TCP packets, essentially. So we conduct IPOF measurement on the server side and the client side, you know, between them to just get the numbers about what is the throughput of the connection, what is the latency, what is the bandwidth we use to we can manually configure the bandwidth that this link should have, and then we set up network impairments. What do we mean by impairments? Where impairments are manually adding a latency our server and client before sending a packet. before starting the measurement. And then introducing artificial packets. Okay, all these are impairments, increasing the MPU sense. You know, acts that depreciate your network's performance are all impairments. So we are going to, once we set up our network and once we are done with the measurement, we introduce impairments to the network and then we place the performance, those are circumstances. Then we note it down and we evaluate. So let's get into it. So first, we should know how to first create a VPC. Okay, that is the very first step because we are going to do everything in the cloud here. So this is the Amazon's VPC dashboard, and here we are first navigating to your VPC. You have the ability to create a VPC. All right, you can name your VPC. I have already created a VPC and I have named it Lab 2. Okay, let me just show you here for demonstrational purposes how we go about doing that thing. And this is your local IP address, the CIDR convention, that the addressing that any device, any participant in this virtual cloud should have its IP address in this format, 10.0.0.0/24, right? So this, and then tenancy is default, and you can add any tags if you want when you create. That's it. I've already created my cloud, so I don't want to waste resources. So once you create your virtual private cloud, you will get a display like this. Okay, you have a lab 2. There would also be a default created, but we are not going to bother with the default variant. We are just going to bother with the lab 2 variant. So you have your CIDR addressing, and so any device, any participant in this cloud will have this addressing. Once you create the virtual private cloud, the next thing that you need to do is you need to create subnets. All these subnets, this subnet, this subnet, all these subnets, so that you can then create the network. So these are all processes. So you go here, you create all these subnets. I created 4 subnets. Subnet 1 and subnet 2 are basically internet 1 and internet 2. What we used to call internet 1 and internet 2 in our previous lab. So this is the addressing, site addressing of subnet 1 and subnet 2. Then we create 2 separate subnets for the server to connect and the client to connect. For the server, I use 10.3 addressing, and for the client, I use 10.4 addressing. Um, you do have the ability to use the same subnets to same IP to use the same subnet for both internal as well as NAT connection, but it is better if you maintain that distinction. It becomes more. Uh, can put it. Let me put it this way: your configuration becomes more manageable, I would say. So it becomes easy for you to manage. Right? Okay. So once we created this, creating a subnet is really easy. You create subnet, and you have to first select a VPC with which the subnetting should be associated with. Up to then, any subnet that you choose will start with this. Should be within this domain, 10.0.0.0/16, which means the first 16 bits would be fixed, and which means 10.0 would be always be fixed, whereas the next 16 bits would be variable. So you have about 0 to 65,534, I guess. Uh, Approximately 65,535 addresses. Okay. So you can manually create your side your subnet at 10.0.0.0/24, 10.0.0.1/24 slash. So you can create that, and you can. So subnet creation is easy. Okay. So we are done with the subnet creations. Now the next steps are, before creating the instances themselves, we have to do one more thing. We have to create internet gateways. So we go here, and you create internet gateway and name internet gateway anything. And this internet gateway, you create an internet gateway and then you associate that internet gateway with your VPC. Why? To any network outside AWS, the only means of reaching your machine, for instance, say Google, is through the internet gateway. Amazon has its very own internet gateway. In our previous lab, we used my laptop as the internet gateway. So my laptop, no, in fact, my laptop's gateway would be my router. I use Spectrum. So Spectrum router would be my gateway. So for all the instances, my my laptop would be my internet gateway, and my laptop's gateway would be uh, the Spectrum router. Let us map that connection to our case in AWS. In AWS, all the instances that we create, server, client, and router instances, they would have um, their gateways to be their NAT addresses, but those NAT addresses would be connected to AWS's gateway, right? And any external servers, say Google or Google or Yahoo or any other external website that you want to access, can be accessed only through AWS's. So yeah, so that's how the connection works. So any public IP addresses that you use, they all come through the internet gateway, Amazon's gateway. So you need to create the internet gateway, and this internet gateway is going to basically function as the gateway for the entire VPC, entire cloud, entire virtual cloud system. Okay. So once you have created the gateway, you do have the ability to have ACLs. ACL is basically a firewall, but for a subnet. So you do have the ability to do those. And 1 second. Mhm. Every video of mine is limited to 30 minutes, it seems. So I should do it in parts. So now this thing is creating a routing table uh, for your VPC, for the entire VPC. So this is laptop, and you can just create a simple route table and associate it with your VPC. So I have already created one. So let me create my routing table. Ignore the last two for now. Just concentrate on these two. What is this? Any IP address in the world. Any IP address in the world has to go through your internet, Amazon's AWS gateway. Okay? But for any other addresses other than the public addresses, I mean, sorry, let me rephrase this this way. For any address starting with 10 point something, right? The gateway is not this. Okay? It will go through the local route. It will go through the local network. It is configured through local network. Okay. Okay, I can understand this is configured through local network, but what particular instance will it go through? The answer is the router. Okay. So it will go through your local network instead of the gateway, right? For any destination that starts with 10 points. So we are going to add these two initially to our routing table as for the initial step we are done. Okay. So now our routing table is done, our internet gateway is done, our subnets are done, so our VPC is done. Then next step is creating the instances, connecting to them through SSH, configuring them, and once we set up the network, that's it. So yeah, So let me go. Before that, I have to introduce one more thing to you. Your VPC has a feature, right, where you can basically see all the connections that it has using a display called resource map. So it basically pictorially shows you how your cloud is. So you have your VPC here, right, and you have all the subnets that you created. You do have the ability to create a separate subnet for a router, but in my opinion, it does not work. If you want, you can. So I created it just to test it, but I'm not using that subnet anymore. So I'm just using four subnets. My router's subnet is in the same domain as my server. Same domain as subnet one. Sorry, this. So my router is completely internal. My router is connected only to the internal network. It's not visible in the external network. Uh, it is visible to the external network through the public IP that I slapped. Let me introduce public IPs to you once I create the instances. For now, just bear with me. And we have four subnets. Server subnet. The server subnet is the for server. Subnet one and subnet two are the internal subnets which we use for our which we use for our internal network connection. And then we have our client subnet, which is for client snack. Right? All these subnets, all these subnets, they use the routing table written by this for lab for our VPC. The routing tables the routing table has it such that its gateway is Internet Gateway Lab, which is this, right? Okay. So I wanted to show this because this is nice. It allows us to pictorically imagine how our entire network setup is. Nice feature that maybe AWS offers. So this is the nice thing about Project Lab 2 here. AWS has so many features that we can use to help us finish our network setup, finish our network setup, maintain, configure. Your networks would have problems, would encounter problems periodically, and you know, having resource maps like these helps us navigate to the bottleneck quickly and resolve the issues. So this is what I about AWS. Now let us continue to creating our instances. Right? So I've already created my instances, but uh, let me just walk you through how we create our instances. So for creating instances, we go to EC2 console in AWS. We create launch instances, right? What do we need here? We need a server, we need a router, and we need a client instance. So we go here, we name server instance, server video, or something like that. Okay. I'm just going to just show you how it is done, but because I've already created my networks, I don't want to waste the resources. Uh, you create Ubuntu. The latest one that is free is 24, and I think 22 is also eligible. So you can choose an OS to your liking. So the thing is, everything is free here in AWS that I'm going to show, except one thing, uh, which I will demonstrate in short instance. Okay. So architecture is 64-bit because this server is 64-bit. What is AMI? AMI is a virtual instance template. This template basically contains specs about the particular particular machine that you're using, remote machine that you're using. So, for example, if you're using T2 Micro, this T2 mic, sorry, AMI ID is mapped to your OS. Sorry, but this instance type is um. Okay, let me rephrase. Sorry, your AMI ID is a template that contains information about your instance type. Okay, what is your instance type? Your instance type is basically your mission, just like how you uh, um, describe your laptops. So here you have T2 Micro. This belongs to family T2 and it has one virtual CPU and 1 GB memory. Has some pricing features. This is free tier eligible. Okay, so this is free. T2 Micro is free. So we do that, and then for logging into our system, we use key pair instances. We use key pair to securely log into your system. Every time you username and password, you log into your remote machine is tedious, is laborious. Don't have time for that. No? So we can create keys for this. We can show you how a new key pair is created. And creating a key pair is always recommended. So you can name whatever you want to your key pair. And RSA is, I'm happy to say that RSA is actually developed by US. So this particular this is an encryption algorithm. RSA is an encryption algorithm, and one of the scientists was from USA. Here. One of the scientists who developed this was encryption. So this is encryption standard. And you can use this encryption standard to encrypt your serials. Basically, how does this key pair thing works? Well, you have a key, and when you have a key, you have a private key, and Amazon has a public key. So whenever you log in into your device, okay, this private key and this public key mingle and it allows you to log in. So that is how the key pair scenario works here. Okay. So it outputs your key, your private key in two formats. This is for open SSH, one is for putty. You can select whatever you want, but I use Windows PowerShell, so I go with open SSH. So you can use P, right? So you create a key pair and new key pair is created on the server. And then what are the other configurations that you need to go to edit network settings. You need to have your instance set up in your lab 2 VPC. That is the cloud where you want your machine to be in. You do that. Sorry. Okay. You do that. You select that. And then what subnet do you want the server to be? By default, your NAT interface is your default network interface. Okay. It should always be the case. Okay. In our previous lab also, when we went to settings, let me show you this. It is always great if we show you the previous section. Okay, you go to Oracle, okay, virtual box, you go to settings, you go to network, you see the adapter one is the default one here. The default adapter is always attached to that. The same case is being repetitive here. This is the default subnet that you're going to use for server. Okay, the NAT. And the NAT is going to be a default interface. It's zero. Interface number zero. So you do that. And then for firewall, you create a security group and uh, you add some rules, security rules. The first rule is always SSH. It follows TCP protocol and port ranges. The port number is 22. Source type anywhere. You need to manually add here in the source. Here it is not visible because let me. So three. This is by default, so you don't need to do anything for this. What this implies is any address can connect to this network 0.0.0.0/0 from any source. You can connect to this network using SSH. SSH follows TCP protocol. For that socket, you use 22 as the connection port number. Then you add another security group rule. So this is for TCP. You basically allow all TCP here in this instance. I'm allowing all TCP paths to go through. So you 0.0.0/0/0 here. The same is for UDP. So you add another security group rule for UDP. All UDP you allow basically allow you allow all the addresses to go through this. All the addresses in the world access to have access to this. It's not recommended. For this, I'm just demonstrating. For this purpose, uh, I followed this. Okay, for all ICMP4, do the same thing. After that, you have network interfaces. So one sec, 5 more minutes. Okay. So for network interfaces, we basically add the first one is your default interface. It is mapped to this subnet, meaning the server sub. Then you add the interface for subnet one, right? Subnet one is this. This is the internal internet one subnet. We use internet one is our convention that we used in our previous lab. So I'm following the same convention. This is for our internal this line, this subnet. Okay. So I'm using this. And this is for network interface two. Okay. That's it. Why are we not able to add any more network interfaces? Well, because T2 micro has a maximum of two network instances that you can add. That's it. And then that's it. You can configure your storage, and once you create launch instance, you uh, launch the network. Right? I'm not launching here because I have already created one. You can also do the entire all the entire process in AWS in AWS CLI. You know, using PowerShell, you can remotely connect to AWS through CMD through CLI. And then you can create the network instance, create the device instance. So that is also another valid way. So you will follow the same process for client and server. So we show you, so I'm not going to show you how the client and server router are done because it is the same procedure as server. But for YoS router, one important thing is you set the image to be YoS, and when you select YoS, you don't have any free AMIs here. So you do have free trial, so you can use this or you can use this. Okay. The thing is, YoS is free. The problem is you don't have a free. You don't have T2 micro is not T2 micro by default is it's not mentioned in this. Mentioned that it is being supported by YoS. So it is being supported to YoS. So one sec. So let me go launch instances. Let me make something. This is YoS. And I click. I select this. It asks me to subscribe to select this. Once that is selected, YoS is successfully selected. By default, C5 enlarges the instance name that is recommended for this, which is not true. You can use T2 micro, but by default, C5 enlarges the option that is being visible on YoS. Use YoS. You don't have T2 micro here. Okay. There is a way posted by my site to use Amazon AWS CLI to get T2 micro, which is supported. But that is a bit tedious to follow because you need to open CLI and you need to. This is good to the eyes. You have a good GUI that you can just directly, visually interact with it. So yeah, that's it. So this is one thing that I wanted to show. And CFA large allows you to have more than two network interfaces. So, but that is not required. Right? So that's how you set up the instances. So this is I followed that video to basically use YoS router with T2 micro instance just for just I wanted to try it out. You can very well use you're comfortable to use CFA enlarge. But the important thing is CFA enlarge is built. It is about 10 cents per hour. 10 cents per hour, yeah. And that's it. So we have successfully created our instances. In the next video, I will walk you through how we are going to proceed with slapping public IPs to these instances, and then SSHing into it, and then setting it up, and then establishing the connection. That's it. Guys, welcome to the second video on the W542 Lab series. This is the part 2 of the Lab 2 video. So in the previous video, I showed you how you create how you um, create the instances, how you first create the VPC and then create the instances in that VPC and allocating subnets and all the nitty-gritty details. Now that we created the network, we can SSH right into it and then do some configurations, and that's it. Our network is set up, and then we can start with our measurement. Raise the network, raise the performance of it. So first we go to the EC2 instance. Okay. Before that, I would like to show you how I did my configuration. My configuration. So once after you created your instances, okay, before showing my configuration, after you are done with creating the instances, which I ended my last video with, you go to uh, public. Actually, you can do it in VPC console. You can navigate to VPC console. Go to just to think about Elastic IPs. Yes, Elastic IPs. Elastic IPs are allocated by Amazon servers. These are all you can just you can just choose your region. Choosing US West 2 Oregon region missions. Missions are situated in US West 2 region, Oregon region. So I'm choosing this region, and you can just allocate. You can just allocate an address for this. That's it. This will be allocated. The only thing is IP, public IPs, you have to be really careful because the global IP pool is really less. So you need to be responsible, and you need to use those IP addresses. And once you're done, you release it back to the pool. So first, once you created an IP, you have to manually select it, and you have to associate that address to a particular instance, particular adapter of an instance. And then once you're done, okay, so once you're done with that, that's it. A public IP is linked to that. So once you're done, okay, what you have to do is you first associate, like if you're no longer if you no longer if you no longer want to use this address, this public IP, you can dissociate this, and then you can release it to the pool. That's it. You no longer be built. So if you just leave it disassociated, the IP address would still remain in your account, and you would be built. It's as good as not using it. It's as good as using it continuously. So be sure to release the IP address once you are done with that. Okay. Best responsible network. Fine. So go back to once you are done. So here, what am I attaching the elastic addresses to? This. One second. Okay. So this NAT, since I'm going to SSH into this machine remotely, this machine is remotely separated away from me. Um, like the previous case where everything is basically stored in my laptop. I need to use this public IP to connect to it. So what I do is I basically map this NAT address to the public IP. That's it. So you go here, you can see my address. This is okay. Go to instances, and you can click instance ID. You can click instance ID to view about that machine. So this has two interfaces, this two IP addresses, and you can go to networking here, and here you can see that interface 0. This is network interface 0, and this has the NAT address. This NAT address is being mapped to this public IP, elastic IP that we just generated. Okay, and this is the private address for the server. Okay. That's it. So let me show you how the thing is for client too. Okay. You see, this is for client. This is for client, and then for the router. I'm using the CPN lot, so it's a free router. Go to network. There are only two instances and one local address. is itself being used as the NAT, used as the it is basically mapped to this local address is itself mapped to the public IP. You can do that. Even though it is not the best recommended, it is not recommended. You can do if you are particularly constrained using 2 micron. If you want to do it free, then by all means you can use it. So this is the public address that's mapped. So, okay. So now that we are good with the interfaces and we have the system ready, we have the topology ready, we have this topology ready. Now we can connect to our machines. So we can go to PowerShell, set, can once you go to PowerShell, you can just SSH into your machine, SSH-I. What is your key? So what is the PEM file that you stored? Enter that key for the server when you created the machine. And then server is using Ubuntu. So Ubuntu, what is the public IP of that address? It's, right? So you copy that, you paste it in the server. We do the same thing for comment. So you go to downloads. My keys stored in downloads. That's why I'm navigating to downloads. And then you SSH client key. SSH into the machine. It's using YOS. So YOS covers the address 44, 834, 195, 122. Okay. So that's it. So you have your router, server as well as now. So what you have to do is importantly we need to set up the connection. Right? So anything to the anything to the client has to go through the router. I've already finished the setup to navigate it through the router, but what you have to do is you have to manually add the IAM root add. Here you can show config to see its network configuration. So this is the default NAT. This is your you know first local IP interface one, and this is loopback interface. Same for client. Config for client. You see this is the NAT address and this is the root address. Okay. For router, you can do if config or you can also show int interfaces. In the first interface, um, you have the first subnet, and in the second interface you have the second local subnet, but it has only local subnets. This first subnet is being used as the NAT2. So you can just type if config, and you can see there are about two interfaces, and the first one is itself being used as um, the NAT. Okay, as well as the internal IP. So the next thing is we have to check. So what's the next thing? We have to manually add the route to route any packet from server go only through the route. So you can just say route add route. I do not remember the exact command because I've already done it, but it, it just comes somewhere like something very similar like this. You add the router, you add the route. So 10.0.2.0/24, whatever IP address that has this particular notation falls into this subnet. has to go through the gateway of what is the router's first IP address 10.0.1.65. Yeah. So that is the gateway through which the first instance has to go through. Similarly, for the client, for any address starting with 1.0, you program it to go through the client's second, the router second interface, which is uh, 2.140. 2.140. It is possible. That is doable. And once you are done with those configurations, you can trace route to the client from the server. Okay. The IP address of the client. You can see that it goes through the router's interface, and then this is the router's interface, and then to similarly we can do the same thing from client to trace route to see. But I faced a very major problem. Even after doing this, I was not able to uh, make it go through the router. So I searched and I tried several configurations. Maybe it has to do with the subnet because I was able to ping from server to router client, not from server to client. There was instead a direct connection, which I did not understand why. Then I deeply analyzed and I was able to navigate to the cable of your VPC. Okay. Ideally, it should work, but it is not working. So what I did is, as a workaround, I went to the where is the routing table? Yes, in the routing table, they mentioned you these two special destinations. This is when we are going to add this. What you do is you basically follow the this command, the route add here using GUI. But this applies to the entire VPC. Okay, that is the only disadvantage of this method. But this solved the thing for me. So what you do is to any destination. Okay, to any destination starting with one, which is the server subnet, use the router's interface two. Okay? What is this? You can check. So you go to router and you see it has two addresses 0C. Yes, this is the interface 2 of router, interface 1 of router. So this interface 1 is connected to the subnet 2, and any packet originating from subnet 2 destined to subnet 1 should pass through this, correct? Should pass through the second interface. That is what I do. And basically vice versa from the server to router. Any address originating, any address destined to 2 from the server, not from server, but any machine in the VPC would have to pass through the first interface of router. So after manually configuring this, it works. It works. So I'm not able to exactly pinpoint why, because manually doing it in the CLI for that instance would work. That is what should ideally work. After doing this, after adding this, after adding these two commands for the entire VPC, it worked. Which is not a recommended thing in my opinion, but it worked. So I was forced to do it. But I would be interested in knowing more about why this worked. So anyone who is watching this video can share in the comments why you think this worked. So after adding this, my tracer worked. So this is the biggest thing that I wanted to share. This is the biggest thing that was bugging me when doing this project. I wanted to share this. So details. Oops, this is done. Very importantly, what you have to do is for every instance, you have to manually say, for example, go to your instance, your router instance, and here in the instance and functions, networking, you have to disable this source or destination check. What it means is basically you enable IP forwarding. You make it to act like a router, like selfish uh, node, which basically just route, which basically accepts and transmits packets destined where it is a participant, where it is the uh, so source or destination. It does not forward. It does not act like a forwarder. Okay? If it is a member in the communication instance, then only it participates. That is why I was able to ping from router to server and server to router, but not from server to client. So router to server and router to client, and vice versa, but not server to client because the router was not acting like a forwarder. You have to change this, and similarly for client and server. So once we did all these things, the network is completely configured. Just a second. Okay, I have 15 more minutes remaining. Okay, so the network is completely configured, and we can start our measurements, so to speak. So we clear the clutter. Unfortunately, cannot clear something here. No problem. Because Debian 64 doesn't have a display. So let's get right to it. So now we have to start with measurements. Okay, so what are the measurements? So you first simply use iperf. Okay, so iperf basically is a software that tests your system, tests your network connection. The server will act as the server. So iperf server. Um, so what's the command I used? One sec. So this is the command I used to basically make the server act as a server. Okay, and the client will connect to this, and then it will send some test packets to to establish the performance of this network. Performance of latency. What is the latency of this connection? What is the throughput of this connection? What is the bandwidth that this connection was connected? The bandwidth that this connection has. Bandwidth is a fixed thing. We set it by default. The bandwidth is I think it's 1 gigabytes, 1 Gbps, but we can program the bandwidth here. Which means 100 megabytes. So you can use UDP or TCP. For you, if you want to use UDP, what you do is you hyphen U. Oh, sorry, this is for server, right? Sorry. The server side, you don't configure bandwidth. Sorry. You just bind this particular interface to this address, then you start. The server is listening. Now, similarly, you do IFF, you are sending a UDP packet, okay, hyphen U. The bandwidth of the connection is 100 megabits per second. You bind the interface one of your client for this operation. If not, it will use the NAT interface. Okay, and the connection will be established from NAT interface. For some reason, my NAT was not allowing UDP packets to go through because of security reasons. I was unaware of that. I was just trying to see my connection, and my UDP packets were not going through. Then I figured out, okay, the port is the connection, the interface is different. So I have to manually bind this interface. This is the interface for which I added all the security rules. Okay, all the security rules. So I bind this, and then I run this connection. You see, this the connection is 100 megabits per second. I mean the bandwidth. Let the thing complete. Now you can see there are also packet loss in UDP. The bit rate is 100 megabits per second. Generally, UDP has no congestion control, so um, it is essentially unmonitored, uncontrolled. So it blasts off, but it is not reliable. If you don't get the packets, it's not. Now, You can do the same test but on TCP. For TCP, we'll use a different port. Yes. So in for 6000, you host the server. Then you do a test for the same network, same bandwidth, everything same. But you use TCP. So for using TCP, you remove the hash U2, hyphen U flags. That's it. Okay. This is done. So you can see the TCP connection is a bit varying, just like UDP. But yeah, for very small bandwidths, TCP and UDP they don't differ. But let us try what happens if we use a very huge. You can see the congestion window too here being adjusted. It's just fixed 149 kilometers, right? And there's just one retransmission, but mostly there are no retransmissions. Okay, now let us do the same thing. Okay, first we did UDP, then we did the TCP. Now again we switch over to UDP, but the change we make here is increase the bandwidth. And let us take at very low bandwidths, UDP and TCP perform the same, but at high bandwidths is where you see the changes. 2000, not 20,000, sorry, 2000. The same thing here. 6,000. No, it is a UDP connection, so sorry. Press, start. That's it. Okay. Now, one second. Ports 7,000. So 2000. Okay. Oh, let's just retry. Okay. This is TCP. Sorry. Okay. Okay. Let's just raise this. So you have a uh, 2 gigabytes per second bandwidth, but the bit rate is very low. It's just half 1 gigabits per second. Right. So you can see the congestion window is also varying. So TCP does a lot of retransmissions at very high level. Life increased bandwidth because the throughput increased, but along with the increased throughput, you also have missing packets. And as you increase the throughput, you have a higher probability of missing your packet. And why does increasing throughput translate to higher packet loss? Because maybe intermediate router that is queuing up drops packets due to increased throughput, right? So that is one reason. So queuing is a very big reason. The intermediate, router might be a bottleneck and it is dropping packets, or the, the receiver's buffer size is not enough to accommodate this data rate, right? So many reasons. Increased throughput always is bad for packet loss. So we can get over. Yeah, this is a fact. Okay, now we do the UDP. Okay, one second. Let me stop the thing here and let me start it again. Now I'm going to test UDP here. So what's the difference for UDP? You do hyphen U. That's it. You see, UDP sometimes has a higher data rate than TCP. Yes, but it will suffer 26% loss. Right? This, in general, it is varying, but typically, traditionally, UCP will have a higher data rate. Okay. For the first instance, UDP had a higher data rate, which every packet got through. Whereas for the second instance, I think it lost about these much packets, 26%. But in average, if you take the average of both these tests, you can see UDP performed better in throughput, whereas it performed very worst in loss percentage. Whereas TCP has zero loss, but it has so many retransmissions, 25. Just a second, let me test how many minutes I have. I'm sorry, the limitation of this is limits every video to 60 minutes. Minutes. So 5 minutes remaining. Okay, so let's go here. Okay, let me stop the process. So let's release 60 seconds. Uh, Sorry about this, guys. Sorry about the silence. I think my computer is a bit laggy here, so I'm just trying to solve that issue. Just okay. This is working. Okay, this is working. Okay, just sorry. Right. Okay. So we're back. Okay. We just have 5 more minutes, 4 more minutes for this video, so I have to do one more step. So let us start introducing impairments to the video, and in the next video, I will complete the impairments part. So here, the next step is okay. The initial we got some action, we got some parameters, we got some performance numbers, not parameters. Sorry, we got some performance numbers for the initial connection. But in the second part, what we have to do is go to the report. In the report, asks us to execute this command. What does this command do? What is QDisk? QDisk is a queuing discipline in uh, it's a queuing it's a queuing discipline that is implemented in Ubuntu systems, where you manually add a delay of 100 milliseconds from the source itself. Okay, so you just delay the entire transmission by 100 milliseconds from the source itself. Right. Stop this command, and you have to paste this in the server as well as client. Start listing. Let me add it to queue this. So you follow this queuing discipline. Start. We are doing everything in interface one, and instead of each zero, we say ENX because this is Ubuntu 24. So the conventions changed, the notations changed. ENX one, two, net, one, net emulator delay, 100 milliseconds. Let us do 100 milliseconds here. Seconds. Because the queuing discipline has been on. You do the same for your copy this. We just first we do UDP and then TCP. Okay, guys. So server start. Okay. Just always keep 2000 as the bandwidth because at higher bandwidths we can see the difference clearly. The client is started. Okay. We just grab some water here while this test is going on. Okay. We have very few minutes left, guys. So let me discuss the results in the next video. Start it. All right. Let me go to it. Okay. Okay, guys. So last we discontinued here at this point. So we introduced the delay and we completed the test for UDP. Now, if we see, uh, UDP has about received UDP has a data rate of about 6.645 megabits per second. The data rate has been severely limited. It has been reduced. So and about 65% of the packets has been lost per total data grams. So this is the amount of data grams that have been lost, and this is the number of data grams that have been totally passed. So 35% have been successfully received. Very worst uh, performance in terms of reliability, but decent, you know, possible to understand releasing an artificial source. We can call it like a literacy. So now we stop and we do the same for TCP. Okay, so we start the server, but TCP is we hosted on server. Okay, start it. Now go to client side, and now you do the same thing, but you remove the hyphen U flag. Okay, and the port to 6000, and you do it. Okay, I can easily see the data rate is being severely limited. Severely limited. Ah, man. If you just compare it, you get about 93 point something, 167 retries. Okay, 93.8 is the net average is the bit rate, but let's just take average to be say some 94. Okay, compare it to your previous TCP performance. It's one. So now, if you're using a delay, it's like one tenth. TCP suffer a much worse performance compared to UDP. But absolutely, there's been nothing. There's been no packets that have been lost. Whereas in UDP, you have so many packets that have been lost. Right. So yeah, it's the trade-off between using TCP and UDP. Yeah. By virtue of network architecture, you can say that TCP has congestion control. So it has congestion window. You can see this with your bare eyes. So it adjusts its congestion window size to allow for if there is a heavy congestion going on, it reduces its congestion window uh, so that you allow your throughput would be limited, your throughput would be throttled down, and if there is good reception and if there's not much packet loss going on, your congestion window size would be limited down, uh, decent throughput. Okay, so TCP is following AIMD, additive increase in multiplicative decrease. So whenever it misses a packet or whenever it encounters congestion and due to congestion it missed a packet, multiplicatively decreases the. So that's the bad thing about TCP. Whereas UDP doesn't have anything like. So an UDP participant in a network consisting of nodes all using TCP, that UDP sender would benefit the most. It would be a very unsymmetric benefit for them. It's very you can say by virtue of network architecture this is very immoral, but this is how it is. The network architectures have been designed. Okay. Right. Okay. Enough for the story. We go back to test. So we reduce delay. Let us go back to the next, which is using a packet loss of 10%, but changing the delay back to zero. Okay. Let's do this. Okay. This is the server. You stop the instance running on the server. You just a second here. Okay, sorry about this. There's no device called EXA. So we have to change it to ENX1. Why ENX1? ENX1 is the local interface. First local interface. ENX. ENX is because of Ubuntu 24, and 1 is the interface that we are using for our local function. 0 is NAT. Right. You do this, and we go back to the print. Just a second, we can copy this. And you go to command, you do this, you paste it. Oh, sorry. So- Oh my god. Sometimes I hate this. Um, so this command is being executed. Now there's no zero delay, but you have a packet loss. Okay. So now what is your guess? My guess is UDP won't suffer here. UDP won't throttle down its rate because it doesn't care about loss. Whereas TCP, hmm. So you host a server. So let us first do UDP. That's the convention we follow. Yes. And UDP. Right. 1000 new. Sorry. What? So issue that we encountered here. Uh, one sec. Let me. Sorry. I think there was some issue. I did the test. Sorry. This is the test. So now you can see that UDP did not suffer much in its data rate. It's just it's plain. It's just 931 megabits per second, right? Uh, but instead of 10%, the data packet loss is even more, 22%. UDP doesn't care, right? But if you reciprocate the same for TCP, what happens? Now that is the interesting thing, right? So go 6000, run the operation on 6000 port, you host the same operation 6000, and now you do the TCP flag, change it to 6000, you run it, it's this amount of inputs, okay? And then because of the artificial intelligence particles, you can see that bit rate, how do you say, it downgrade to, performance was worst, abysmal. And the was abysmal compared to what we should have. 2 gigabits per second is the bandwidth that we use. We set up the link, and we are just getting 12 because we have a 10% packet loss, and TCP collapsed in this case. The data rate down. But yes, we have very reliable transmission, but the data rate is very abysmal compared to what we get in UDP. UDP has about 700 megabits per second, so UDP doesn't care. But in these cases, I would say if you if you prefer uh, if you prefer you know, more data rate over reliability, go with UDP. Because if reliability is the thing here, say something like an important email that you send to your professor, obviously you need reliability. You need the messages to be transmitted as you transmit it. You don't want it to be mishap. Trust me on that. So in those cases, TCP is the thing. But for simple things like mail, yeah, it's okay. For very data intensive stuff happening, say if you want a video where you don't want to lose any information, something like that. Uh, you really need a good data rate and you so don't want to miss information. In that case, um, you want to use TCP here, but that thing is abysmal. The data rate is abysmal. So there are many hybrid protocols that you could use to say something like quick QUUCI. We are going to implement a hybrid protocol like that. Before this is just a brief intro to that. Um, so this is what we are going to do. So that's it, and we are going to carry out with the tests. Yes, can test this if you want. Kernel links. Then what are we doing here? So this is for deleting the set configuration and um, removing everything down. Right. So this is for deleting the set. But before deleting the set configuration, you can do that R first. Yeah. Okay. You do that. You delete this. You delete all the changes that you made. If you delete all the changes that you made, it will default to the default status and the network was first established. Default state. The network was first established. So you copy this. Sorry, ENX1. Much more. So all the configurations. It is something the same for mine too. You this map. This what is this going to do? It limits the data rate to 100 megabits per second. It introduces a latency of 1 millisecond, and your MTU size. Your MTU size in this case would be limited to 9015, right? So all the three things in one line. What is the limitation of increasing the MTU size? Increasing the MTU size, what happens is if you miss a packet, if TCPI wants to retransmit that packet, you want to transmit the entire stuff again, and transmitting a larger packet again will obviously bring down your data. So that is bad, right? So yeah, that's the hint that I'm getting. I'm seeing this club. If whereas for UDP, I won't think. I do think UDP will get to suffer because the data rate is limited. You see, it's 100 megabits per second. But other than that, I think UDP doesn't care. Yeah, I think you would get data rate for which just it's just it. So we go here and we change to ENX. So we add this command, right? We copy this and we execute the same for the client side too, right? So carry on with this. So what's this? So Let's do an UDP we go with the convention. So start now. This change the port number. It's the performance. I think it's oh all right. First 95% of the packets in the second instance, and it has a data rate of about 100 megabits per second. Bandwidth is okay. The data rate is I thought the data rate is limited if we add this. Was it not limited for UDP? Okay. Sorry. I think this is the difference that we should look. It's about 98 megabits per second, and it's about 95%. I just forgot about what is jitter in UDP. Let's check it out actually. Variation in delay. Okay. It's just a variation in your delay. So, so if your connection is jittery, I think you have a lot of things happening. Okay. The router has maybe if the router is dropping some packets or something happening in throughout that link. So we have heavy jitter. Zero point 0.4 millisecond of jitter is say reasonable. Okay, but it is losing 95% of the packets in this case. Interesting. Let's do the same experiment for TCP now. So TCP was 6,000. So we started and what 6,000 flag, right? It is limited. It is being limited. It is slower than UDP, of course, but I would say TCP is the winner here. Just 4 megabits per second. Does it make a difference? Okay, it depends. Okay, this is the observation. TCP slows down by 4 megabits per second. It has tremendous amount of free price. It is limited by 100 megabits per second, so we can't really complain why it didn't go beyond that. Right? Even though we gave a bandwidth of 2 gigabits per second, but due to packet loss, uh, TCP collapsed slightly. TCP didn't collapse, but it got slowed down. Whereas UDP, it doesn't care packet loss. Um, I do wonder why in the first instance it got 2 gigabits per second. Maybe I should only, oh, this is for 2.33 gigabytes and this is for 117 megabytes. Okay, this is the bandwidth. Okay, all right. This is the shown data rate, I think. Because for TCP, why is both of these instances about 112 megabytes per second? Interesting. We should only see the second one because it's for the same interval. Let's stick with the last. This is the convention that they followed in YouTube videos. Okay. Just losing 95% of the population in UDP. It is very worst. It is very, very bad. So last test. That is just a second. If we go back to the document and running this command. What is this command doing? Well, it is. What is this command doing actually? Let us see. Actually, let us go to GPT. It does say what it is asked. What is this command doing? I'm interested in knowing more about this because I wanted to show you one specific thing. So this command is useful for increasing the speed of the network interface to 10 megabits per second. So you manually see, here is the very important thing. You manually change the speed of the network interface itself to handle 10 megabits per second. Okay, network interfaces, you are actually having a virtual interface. Okay, but the device would have a physical network interface, the network card. Okay, the network card would have interfaces. So you're trying to change that virtually, remotely, right, for the AWS instance. Well, what happens if you try that? Let us try it. Stop this. Paste the command here. So instead of sudo, let's go here. Let's go to sorry, let's go to this is it. Let's go to the report and we can type it as it is. Sudo it's tool, right? ENX is one. ENX1 is our interface. It's where we want to increase our speed to 10. This is you are doing a physical process, a manual process. The ultimate effect of this is the OS is trying to control the network. Okay? And the network card is a physical device, electronic device. Okay, and the OS is trying to control the network, control the electronic, control and electronic parts, electronic parts output. Okay, let us put it. And you're doing this virtually to a virtual machine, right? Machine that has a virtual layer on it. The virtual layer is the OS layer, the Ubuntu layer. First, you have the Amazon machine, physical machine, and you have the Amazon machine instance, physical image instance, um, a hypervisor, and top of that you have your Ubuntu OS layer, and you are controlling it remotely, and you're trying to configure Amazon's physical network interface that is present in Amazon's physical machine. So, sorry, this one speed, the speed to 10 megabits, operation not supported. And obviously, AWS wouldn't allow that. It's their mission, so they have the complete control over it. They don't want to allow external people to manually to alter uh, their network configurations just remotely, just virtually, unknown people. They don't want they don't want personal users to do that to their missions. You can contact Amazon regarding this if you want. AWS regarding AWS personal regarding this if you are a network enthusiast or an engineer who are from uh, from an industry who's working on manufacturing network equipment. And if you want a specific configuration, you're using Amazon's cloud for something, and you want this particular configuration, you may request it. But by default, it is not allowed. It doesn't. Amazon doesn't allow a simple OS to manipulate the speed of the network interface, which is an electronic equipment. The network card is an electronic equipment, and the interface is an electronic, is a port, physical port, uh, like an RF, no, no, yeah, an RF port. and it is done API to software. In software you typically see a port, but that port, it's just virtual port, but it is physically connected to. It is being mapped to a physical port, which is an electronic port. So software ports and physical ports are different things. You can try to do the same thing in client too, and it won't support. So yeah, that's it. So well, let's do one more thing. We delete all the configurations that we made once more. Sorry, the configuration. Same for client. Okay. Now, instead of causing these impairments for the server and client, which are the endpoints, you basically cause the impairment in just one instance. What is that instance? In Docker. Okay. What happens? It is just my assumption. Even before testing it, my assumption is that it is going to have the same effect because ultimately you have a single network. Even if the endpoints, instead of manually configuring the impairments on endpoints, manually introducing the impairments on endpoints, if you add the impairments to the bottlenecks, okay, which is the router in this case, impairments to the router, which is the central point through which the medium through which the packets travel, you have the same effect of causing the impairments on endpoints. Right? So we can test that. So we can just for starters, I'm just going to show you this because for other things too you have the same effect, but I'm just going to show this for demonstration. So you copy the first command, you go to router now. Okay? You navigate to router. Just router. You have nodes. You go to router. Um, um, so what is the command? Sudo. Okay. Sorry. You have to record this now. Okay. So sudo pc qdis. It's a queuing discipline, right? E zero or no, we are going to add this to the non-elastic to the interface that is non-NAT or the interface that does not have an elastic IP. So what is the interface that does not have an elastic IP for the route? This instance one. So we are going to do it. That is what uh, the report indicates. So not the elastic IP, that interface. So we can do that. Sure. So you go to the OS version, you navigate to the report. If one, this is Debian, right? So we use it instead of ENX. And if one, what else? If one root, let let them delay 100 milliseconds, right? You add this. Now that's it. You don't care about the router anymore. Clear everything. Same commands again. So first let's do TCP. Or okay, first sorry, we go with the convention, right? Okay, first let's do Unity. It's the same to me, same performance. Let's do it for TCP. Just introduce the loss of, not loss, sorry, delay of 100 milliseconds. TCP support heavily here. Yeah. But yeah, that tremendous number of retries for the second packet. Second packet forward. So the overall effect is the same. Instead of doing the instead of doing the impairments in the endpoints, you can just add the impairments, all the impairments to the bottleneck, and it's just a one-time task. That's it. Okay, guys. So thank you for your attention to this video. Let me come back with lab 3.